guys, it's Miss Miklos, and if you guys open up your note handout for 3.1, today we're talking about exponential functions, and we're going to see in class really how quickly an exponential function increases or decreases. But we're starting with some calculator problems, so I figured I would just start here with my calculator. So we're going to go on over here and start with something easy, 4.8 to the 6.1 power. I'm putting 4.8 in parentheses here, and then caret to the 6.1 power. So I end up getting an answer of 14,307.757 because it tells us to round 3 places after the decimal. Number 2 is a little bit different. It says 7 to the negative 2 pi power. So I know my negative is down here. To get to pi, I'm going to press second caret. We know pi is an irrational number. And I get this weird answer here of 4.899. And this, just a reminder, means times 10 to the negative 6th power. Okay, so whenever we get that strange number, that's telling us that it is in scientific notation, which a small number would make sense here because we know a negative exponent means it makes this into a fraction. Okay, number 3, we have 14 to the square root of 3 power, which gives us 96.639. And number 4, we get to something kind of weird. We get to where it says e to the first power. And if I talk about pi, you guys are really used to pi. That's an irrational number. And we know it's a number. Okay, pi isn't just a Greek variable or a Greek letter. It really represents a number. And e is very, very similar. We call it Euler's number. So the way we get to e is if you press second ln. Ln stands for our natural logarithm. And I'm going to do e to the first power, and it tells us it is 2.718. And what we will see is this is another number that repeats quite frequently in nature, and we're going to use it a lot this chapter when we deal with logarithms. And so they actually give it a special name as Euler's number, or e. So if I'm going to do e to the 2/5 power, I'm going to press second ln. And I'm going to go ahead and put 2/5 in parentheses just to be on the safe side. And that tells me it's 1.492. Number 6 says cube root. And I want to show us 2 different ways we could do this. If you press math, okay, option number 4 here is a cube root. So I'm going to choose cube root of 41. The other way that you can do this, our answer is 3.448, is if you typed in 3 and then went to that math option again, notice that 5th option down has an X where the index number should be. What that's going to do, it's going to make whatever number you typed first into your index number, and we get the same answer regardless of which method we use. Okay, 7 through 10, if we look, all of a sudden we're starting to talk about log and ln. Log base 10 of 400 is how we would read number 7. Okay, log base 10 of 400, log base 10 is what we call our common logarithm, which is just log. So I'm going to type the log button and then type in 400. And what a logarithm is, it is just another way of thinking about an exponent. Okay, so this is saying the log of 400 is 2.602. Now I can only use this log button when our base is 10. So number 8, we have a base of 10 again, so I'm going to press log of 3.821. And we're going to spend a lot of time kind of talking about how a logarithm is an exponent. But what this is really saying, I'll actually tell us now, log of 400 is saying 10 to the 2.602 power is 400. This next one is telling me that 10 to the 0.5821 whatever power is 3.821. So what we're really finding is what exponent makes 10 to that power equivalent to the number that we're taking the logarithm of. Now, ln is what we call our natural logarithm. So we have our common logarithm, which is base 10, and our natural logarithm. Our natural logarithm is log base e. So this is like we have a base of e. So ln of 18.42, what that is doing is it's really saying e to what power is 18.42, and we get 2.913. And then lastly there I have ln of 1 plus radical 3. So I'm going to type that in, move my arrow over so that I can get that all in parentheses there, and I end up getting 1.005. So this is how we use our calculator. Now, just so you know, it doesn't matter if you're in degree mode or radian mode, and we're going to be using our calculator quite a bit in this chapter. But now we're going to transition into graphing without a graphing calculator. So go ahead and put your graphing calculator away. Okay, so just to clarify, we read this as log base 10 of 400. Log base 10 is just log, and log base e is ln. Log base 10, common logarithm. Log base e, or ln, is our natural logarithm. Okay, so number 1 tells us graph y equals 2 to the x using an xy chart. And we will remember that whenever we don't know how to graph something, we should use an xy chart. I've already supplied us with some x values here. So 2 to the negative second power, let's just review. That means 1 over 2 squared, which is 1/4. 2 to the negative first power is 1 over 2 to the first, which is 1/2. 2 to the 0 power is 1. 2 to the first power is 2. 2 squared is 4. 2 cubed is 8. So what we really just did was find a bunch of ordered pairs that are solutions to this graph. Or I should say they're solutions to this function. Okay, so I'm writing down all these ordered pairs, and we're going to go ahead and graph them over here. So I have -2 1/4, -1 1/2, 0 1, 1 2, 2 4, and 3 8. Now, what makes this difficult is I think it's pretty easy for us to understand that it's increasing quite quickly over here. We can see this does not really look like any function that we've graphed so far. The tough thing for me is it's difficult for me to see as we go to the left what is going to happen, and what we are going to eventually figure out here is that this is never going to cross the x-axis. And the reason being, if I put in something like -10, 2 to the negative 10th power is like 1 over 2 to the 10th. So it's just becoming a very, very small fraction. It's getting closer and closer to 0, but it's never actually going to touch 0. Okay, so there is what this would look like. Now at y equals 0, okay, I'm drawing a dashed line here. And we call this the asymptote. And you guys worked with asymptotes a little bit last year in Algebra 2. And what an asymptote is, it's a line that our function approaches but never actually touches. Okay? Later on in calculus, unfortunately, we will blow your minds and you'll learn that you can touch it. But as of now, that's what it is. So it says, use the graph to predict the value when y equals 20. Now what makes this tough is I don't see when y equals 20, but I'm thinking that x is going to be between 4 and 5. And I'm just using my knowledge that 2 to the 4th power is 16, 2 to the 5th power is 32. So it's going to be between those two values. Now it's telling us to sketch a graph of the reflection over the x-axis and write the resulting equation. Okay, so we know over the x-axis means it would look something like this. And mine isn't perfect in all the points, but that's okay. The main thing we need to remember, we're actually shockingly building on what we've learned previously. And I know a reflection over the x-axis means I have a negative outside my function. So this equation would be y, or f of x, equals negative 2 to the x power, or the opposite of 2 to the x power. Number 2 is asking us to graph y equals 2 to the x, and I promise you we're going to get real good at that. If I can actually get a pen, here we go. So I'm going to go ahead and plot those points again. Okay, and this time it's asking us to do a reflection over the y-axis. So this time, if it's over the y-axis, that means I should fold on the y-axis and it would look the same. And we may remember from our previous chapter that a reflection over the y-axis means that we have a negative inside the function. So this is going to be f of x equals 2 to the negative x. So notice my negative is inside our function. And we actually call this an exponential decay function. Okay, so it's decaying because it is decreasing as we go from left to right. So if we look at this, the intercept of a decay function, and whenever we're talking about intercepts here, we mean a y-intercept. It is going to be 0, 1. It is decreasing. Our domain, if we look back, wow, amazing, we're using all this stuff you guys know. Okay, if I'm just looking at this blue one here, let's get it so it's not quite as crooked. There we go. It looks like it's continuing to the left and to the right. So I'm going to say our domain is from negative infinity to infinity. Our range, though, it doesn't look like we're dealing with any y values under the x-axis. So I'm going to say our range is from 0 to infinity. And our asymptote here is an equation. It is an equation of y equals 0. So that is always going to be a horizontal line. We can't just put a number, okay, because that's not saying what's happening. A horizontal line is a y equals line. So these are the general characteristics of a decay function. Okay, once again, number 3 is asking us to graph our favorite function. So I'm going to go ahead and put those all up there. Okay, there we go. Now it's saying graph y equals 3 to the x using the xy chart. So I'm going to do negative 2, negative 1, 0, 1, and 2. So 3 to the negative second would be 1/9. 3 to the negative first is 1/3. 3 to the 0 is 1. 3 to the first is 3. 3 squared is 9. So I'm going to go ahead and plot those points. Now notice I'm not totally accurate on everything, and honestly that's okay. But it's going to look something like this. Okay, and if we're looking at these, if I'm concluding about the base numbers, so we know the base numbers here are 2 and 3, and we're going to say something like the bigger the base, the more rapid the growth, or the quicker it grows, or something like that. Okay, those aren't exact words you need to have, but I think it just gives us a general idea. Will these exponential functions ever cross the x-axis? No. And the way that we can figure it out is to substitute in x values. So we can choose x values to the left or to the right to see is it ever going to cross the x-axis. And this is what we call an exponential growth function. Both of these are. Okay, if we look, they are increasing from left to right. They are growing and getting bigger. But they do have some things in common. Our intercept is 0, 1. They are both increasing. Our domain is from negative infinity to infinity. And our range is from 0 to infinity. And our asymptote, once again, is y equals 0. Okay, so number 4 is asking us to graph y equals 2 to the x. And once again, we are really, really good at that. In fact, we know what all of those different ordered pairs are going to be. So I'm going to go ahead and graph those on here. So I have -2, 1/4, -1, 1/2, 0, 1, 1, 2, 2, 4, and 3, 8. Apparently, even though I know where those points are, I'm failing in actually graphing them. Okay, there we go. The other thing we know is that there is an asymptote here that it's never going to cross. Okay, so our intercept. We know an intercept, the y-intercept is when x is 0, and we can look at our graph and see it. We can also look here, when x is 0, what's the y value? So our intercept is 0, 1. This is increasing. Our domain is negative infinity to infinity, and our range is 0 to infinity. And our asymptote, as I've stressed numerous times, is an equation, and it's y equals 0. Okay, we should definitely see some similarities in our characteristics versus what we've done on other problems. Now this time, it says graph x equals 2 to the y power. So that means this time, y is our input, x is our output. We are switching x and y. Let's see what that looks like and if we've dealt with that before. So I actually know what all those ordered pairs should be. So I'm going to go ahead and graph those, and I'm going to graph this one in blue. So I have, let me kind of zoom out a little bit. Okay, I have 1/4, -2. So all of a sudden, this one is doing some weird stuff because we have not seen anything that goes below the x-axis, and here it clearly does. We have 1/2, -1. We have 1, 0, 2, 1, 4, 2, and 8, 3. So this time it looks something like this. And what I'm noticing, this time it appears like our intercept, our asymptote is a vertical line here because it looks like it's never going to cross over into the negative x values. And if we look at our intercept, this time there is no y-intercept. Okay, but what we do have this time, we do have an x-intercept of 1, 0. If we look at it, it is increasing even though it looks a little bit different, so I'm going to circle that it is increasing. Our domain this time is from 0 to infinity. And just a quick reminder, the reason why we're using a parenthesis with 0 is because it doesn't actually reach 0. This time our range is from negative infinity to infinity, and our asymptote is x equals 0. So, draw the line of reflection between the graph of number 4, and what does this tell us about the relationship between the functions? Shocking, once again, that we're going to do something that actually relates to what we've learned. But I notice it looks like there is this line here of y equals x that it is reflected over. And you guys may or may not remember, this tells us that they are inverse functions. Remember, inverse functions, we switched our x and our y. And that's exactly what we did here. Okay, yes, we're finally almost there. And this one, we are definitely going to see some interesting things that happen. So it says graph f of x equals 2 to the x power. And so we're going to go ahead and once again plot all those points. I'm also going to draw the asymptote for that particular line just to remind us. It's also a good idea to draw that so when you're graphing this line, even though this is a sketch, we know it shouldn't cross this horizontal line. And I'm also going to label this f of x. Or you could even just write f if you wanted to. Now it says graph g of x equals 2 to the x power minus 2 using the xy chart. Okay, so I have 1/4 minus 2, which is going to be negative 7/4. 1/2 minus 2, which is going to be negative 3/2. 1 minus 2, which is negative 1. 2 minus 2, which is 0. And 8 minus 2, which is 6. And I got all of these numbers by doing 2 to this power. So if I'm graphing these ordered pairs, some things that I'm going to notice, okay, we said it was 0, negative 1. 1 was at 0. 2 was at 2. And 3 was at 6. Okay, and there's g of x. And one thing I noticed this time, it looks like our asymptote is a little bit different. It looks like our asymptote this time is going to be y equals negative 2. And some things that I want to point out here. Okay, we've spent a bunch of time talking about functions and transformations and all of that. Notice the relationship between f of x and g of x is that g of x, every single point is down 2. Okay, every point's down 2. Now, how do you think we would see that? Okay, and what we're seeing here is just like in chapter 1. Whenever I add or subtract to the function, that raises my graph up or down. And the other thing we will see is this constant value is always going to be where the asymptote is. So our intercept is going to be, this time, at 0, negative 1. It is increasing. Our domain is once again negative infinity to infinity, but our range is different this time because we know our asymptote is y equals negative 2. So our range is going to be from negative 2 to infinity. And sorry for the marks there, my cat decided to walk over the screen. If we look at this, okay, if I'm not sure that it's really y equals negative 2, I might want to try and substitute in some of these values and see if it ever crosses negative 2. And we would see in this case that it does not. So it's asking us, how did the number outside the function affect the graph and the asymptote? And we are going to go ahead and say that this is a vertical shift. Okay, and even though we didn't do one of these on our homework, or I'm sorry, on our notes, we'll have some on our homework that might be like f of x equals 2 to the x plus 1. So I just want to think for a moment and just remind ourselves, how does this value inside the function affect it? And this would be a horizontal shift. So what I'm really trying to tell us here, and in this case it would be to the left 1, because we know we always move in the opposite direction. With graphing, we can do one of two things. We can always make an XY chart, or we can use our knowledge that we've learned already about vertical shifts and horizontal shifts to make things a little bit easier.